This gray powder is soda ash sodium carbonate, about $200 a ton, dug from the ground on almost every continent, a close cousin of table salt, though it isn't table salt. People have known for over 30 years you can build a rechargeable battery out of it. So here is the puzzle I want you holding. If it's this cheap and this common, why is it almost certainly not the battery in your phone? And it gets stranger. The sodium ion at the heart of this battery is bigger than lithium's in a crystal, about 34% wider, a jammed key in a lock. Yet wrapped in liquid, that same sodium ion behaves as if it were smaller than lithium and slips through more easily. Bigger and smaller at once. Pin that in the corner. Everything we do today is us solving it. Here's how we crack it. Stripped bare, a battery is just 2 shelves and a shuttle a rocking chair. One shelf holds our ion, the other takes it in, and rocking it back and forth is the whole game. So instead of being handed a finished sodium cell, we'll build one on this empty board from nothing. Choose its ion, its anode, its metal, its cathode, its liquid. And the rule is every part is forced on us by the part before. Start with the shuttle. A battery just needs a positive ion to rock back and forth, and the whole periodic table is on offer. So why not simply use lithium like everyone else? One constraint decides it, and it has nothing to do with chemistry. We want a battery the entire planet can build without fighting over the raw material. On that single test, sodium wins. Here is the reveal that started the whole industry, and it's the strongest number in this lecture. This is how much of the Earth's crust is sodium versus lithium. Sodium is about 2.5% the 6th most abundant element there is. Lithium is a trace, roughly 20 parts per million. Depending on which lithium figure you trust, sodium is somewhere between 500 and 1,000 times more common. It's in every ocean and every salt flat on Earth. Abundance shows up as price. The sodium feedstock, soda ash, runs a couple $100 a ton. Battery-grade lithium carbonate has swung wildly from $6,000 up past $37,000 a ton at its 2022 peak. So on the raw ingredient alone, sodium is 10 to 70 times cheaper. And notice soda ash, not table salt. People love to say these run on table salt. They don't. But abundance isn't only cost, it's who holds the tap. More than half the world's lithium reserves sit in just 3 countries: Chile, Argentina, Bolivia, the so-called lithium triangle. And over 80% of battery-grade lithium is refined in a single country, China. That's a choke point one hand can squeeze. Sodium has no triangle. It's smeared across every coastline on Earth. For a government thinking about supply security, that is the whole argument. One more structural win before the bill comes due. Sodium cathodes can skip cobalt and nickel entirely, the 2 most contested, most expensive metals in a lithium cell. Cobalt alone is about 70% mined in one country, the Democratic Republic of Congo. So far, sodium looks like a free lunch. And here is where hype dies, so let's be honest right now. If sodium is this cheap and this abundant, why isn't every battery already sodium? Because cheap dirt is not a cheap cell. In 2025, a finished sodium cell runs about $59 a kilowatt-hour. Lithium iron phosphate is about $52. Sodium carries a slight premium today, not a discount. The factories are tiny and new. The savings only arrive at scale. Pin that as our open question. Is sodium's cost advantage real or just a promise? We picked sodium for economics. Now physics sends the invoice. Sodium sits directly under lithium in the periodic table, same column, same +1 charge, same rocking chair job, but 3 numbers change between them and every one of them costs us. Weight, voltage, size. Cost number 1, weight. A lithium ion is about 7 grams per mole. Sodium is about 23 more than 3 times heavier. Every single ion you shuttle drags over 3 times the dead mass across the cell. That, before we've even built anything, is a direct hit to energy stored per kilogram. It's baked into the atom. Cost number 2, and watch a misconception break. You might reason that sodium, lower in the group, is more reactive, so it should give more voltage. Backwards. On the standard scale, lithium is minus 3.04 volts, sodium only minus 2.71. Sodium is less negative, so for the same kind of cathode, a sodium cell lands about a third of a volt lower. That metal potential is the single biggest reason, though exactly how sodium settles into each host shifts it a little too. Put those together and you can SCE the penalty. Energy is just voltage times capacity, the area under the discharge curve. Sodium loses on both terms at once, a little less voltage and a heavier carrier. That means fewer charges per kilogram. Draw lithium's rectangle, then sodium's visibly smaller. This isn't a fixable bug, it's arithmetic. So sodium can never win the energy fight, which means it had better win a different one. Cost number 3 is our paradox, half of it anyway. In a solid crystal, sodium's ion is about 102 picometers wide against lithium's 76, 34% bigger. Bigger means more strain squeezing into a host and slower crawling once it's inside. That's the bigger half of our pinned question. The smaller half we have to earn later. For now, remember it plainly. In the solid, sodium is the big, slow one. Now we build. Every cell needs a place to park the ion on the negative side, the anode. Lithium's answer is graphite, neat stacked carbon sheets, and lithium slides between them, 6 carbons to every lithium. Elegant. So the obvious first move is just do the same for sodium. Let's slot a sodium ion into graphite and see. Watch this break. For lithium, packing 1 lithium per 6 carbons releases energy minus 16.4 kilojoules per mole. It's stable, it wants to form. For sodium, the very same structure costs energy, plus 20.8 kilojoules per mole. Positive, it does not want to exist. In real graphite, sodium manages barely 20 milliamp-hours per gram, basically useless. Our copy-paste anode just failed on the board. And here's the trap almost everyone falls into. They say sodium is simply too big to fit. It's wrong. Potassium is even bigger than sodium, and potassium slides into graphite just fine. So size is not the culprit. The real reason is bonding. The sodium-carbon bond is just too weak to pay for cramming in, so the whole compound is unstable. It's subtle chemistry, not geometry, which means we can't fix it by squeezing harder. We need a different carbon. So we throw out the neat lattice and reach for its messy cousin, hard carbon. Not a defect, a feature. Instead of tidy stacks, it's a chaos of warped, disordered graphene fragments riddled with tiny sealed nanopores. And that mess is the whole point. Sodium can't order stack in a crystal, but it can hide in this jumble, stick to all those defect edges, and pack into the pores. Where the ordered lattice rejected sodium, the disordered one welcomes it. Let's draw how it actually fills live. Voltage down, capacity across. First, a sloping stretch from about 2 volts down to 1/10 of a volt. Here sodium is adsorbing onto surface defects and edges. Then, a long flat plateau below 1/10 of a volt. Sodium packing into those closed pores as clusters of almost metallic sodium, and this plateau holds most of the charge. Optimized hard carbon reaches 300 to 350 milliamp-hours per gram. We have an anode. 2 honest asterisks. 1. Exactly how hard carbon stores sodium adsorption, pore filling, clustering is still genuinely argued in the literature. Competing models unsettled. Don't let anyone tell you it's solved. 2. That plateau sits a hair above 0 volts, so charge too fast or too cold, and sodium plates out as metal on the surface, the same danger that haunts lithium. And the first cycle permanently swallows 10 to 20% of your sodium, building a coating. Nothing here is free. Act 2 question, keep it open. We now have a working anode. What's the cheapest metal we can print it on? The answer hides a genuine surprise, and it's one of sodium's very best tricks. Every electrode needs a current collector, a metal foil to carry electrons out. Lithium is forced onto copper for its anode, because at low voltage, lithium actually alloys into aluminium and eats the foil away. And copper is heavy and pricey in a lithium cell. The copper foil alone is about 13% of the whole cell's mass and 8% of its cost. That's dead weight we'd love to drop. But sodium doesn't alloy with aluminium. Watch. Drop the voltage, and lithium fuses into the aluminium and crumbles it while sodium just sits calmly on the surface, untouched. So sodium lets us use cheap, light aluminium on both sides of the cell. Aluminium is a third the density of copper 2.7 against nearly 9 and several times cheaper. We just deleted the copper. Lighter, cheaper cell from one quirk of chemistry. And that same quirk buys a safety trick lithium simply cannot copy. Because there's no copper to dissolve, a sodium cell can be run all the way down to 0 volts and stored and shipped there like a discharged capacitor. No stored energy, nothing to catch fire. A lithium cell can't. Even its empty state sits well above 0 volts or the copper corrodes. There's a whole transport class, UN 3292, for shipping sodium cells safely dead. 2 electrodes on aluminium, now the liquid that carries sodium between them. Good news, no exotic chemistry needed. It's the same recipe class lithium uses, a carbonate solvent blend. We just swap the salt. Cross out lithium hexafluorophosphate, write in the sodium version sodium hexafluorophosphate, about 1 mole per liter, right where the conductivity peaks. Not solid state, not strange. Why that salt and not another? Because the alternatives fail us. Sodium perchlorate is a dangerous oxidizer. The TFSI salt corrodes our brand new aluminium foil. Sodium hexafluorophosphate protects the aluminium and stays safe. Every choice on this board is forced, nothing here is arbitrary. And here, in this liquid, we finally meet the other half of our paradox. In the solid, sodium was the big, slow one we saw that. But out in the electrolyte, sodium wraps itself in fewer, more loosely held solvent molecules than lithium does. Its solvated bundle is actually smaller, and it sheds that coat more easily. Bigger bare ion, smaller dressed ion. Hold that thought because the payoff only lands when we take this cell out into the freezing cold. Not yet. One piece left. The cathode, the positive host where sodium lives when the cell is charged, and where the voltage is really born from a transition metal changing its oxidation state. And here's the twist. Unlike the anode, there is no single winner. 3 whole families compete, each a different bargain. Let's grow the family tree. 3 branches, layered transition metal oxides, polyanionic compounds, phosphates and fluorophosphates, and Prussian blue analogs, iron cyanide cages. Highest energy or highest voltage in life, or lowest cost and fastest, pick your trade. Watch each branch fill in. Branch 1, layered oxides, the energy champs, the closest thing to a lithium cathode. Sodium sits between sheets of metal oxide, and you'll see a notation, P2 and O3. It is not a version number. The letter is where sodium sits, prismatic or octahedral, and the digit is how many oxide layers repeat. P2 has wide channels, so sodium moves fast. O3 packs in more sodium, higher capacity, but slower. They reach roughly 160 to 200 mAh per gram, near 3.1 volts. The catch, honestly, their moisture-sensitive humid air pulls the sodium out and grows a crust, so they're handled dry, and which of the 2 ages worse is genuinely still argued. Branch 2, polyanionics, the voltage and endurance branch. Sodium woven into rigid phosphate frameworks. Lower capacity, only about 128 mAh per gram, but look where it sits, nearly 3.9 volts, in a frame that barely moves as sodium comes and goes, so the cycle life is superb. Remember, energy is capacity times voltage, so high voltage rescues the modest capacity. And here's a myth to kill. You cannot just make sodium iron phosphate as a copy of lithium's LFP. The useful form is metastable and stubborn to make. The form that grows naturally, marasite, has no channel for sodium at all, electrochemically dead. Sodium had to invent its own hosts. Branch 3, Prussian blue analogs, yes, the pigment. An open iron cyanide cage with wide, roughly 4.6 angstrom tunnels sodium rockets through. Fully sodiated, about 170 mAh per gram, near 3.2 volts, dirt cheap and fast. But it packs loosely, so low volumetric energy, and it hoards water and framework vacancies you must bake out. This is a real niche power and life over density. Honest footnote: Natron bet its whole company on this chemistry, and Natron ceased operations in 2025. The field is brutal. That's every piece. Let's snap the cell together and run it. Layered oxide cathode on aluminium, hard carbon anode on aluminium, sodium salt carbonate electrolyte between them. Charge it. Sodium ions leave the cathode, cross the liquid, and lodge in the hard carbon while the electrons are forced the long way round through your circuit. Discharge, and it all reverses, and that electron loop is your current. The same rocking chair as lithium, but a cell we built from constraints, not copied. Now the honest measurement, not a hand drawing. This is a real simulation of a sodium cell discharging from the Chayambuca sodium dataset. Its average lands around 3.1 to 3.2 volts, exactly the range commercial cells report. Now remember that third of a volt from the metals? That's a same cathode statement. Build a lithium cell with the same kind of cathode, and sodium sits about that much lower. But real cells use different cathodes. Against lithium iron phosphate at 3.2 volts, sodium is nearly level. The big voltage gap only really opens against nickel-rich lithium up near 3.6. What never changes is the physics on our board: a heavier ion and a lower metal potential both push sodium's energy density down. So how does our finished cell really stack up? Here's the honest scoreboard next to lithium's two champions, LFP and nickel-rich NMC, and I'll be blunt. Gravimetric energy. The single best sodium cell, Naxtra, hits 175 watt-hours per kilogram, near LFP, but that's the best. Typical sodium is only 120 to 160. LFP reaches up to about 205, typically 160 to 185. Nickel lithium is 250 to 300. Volumetric, sodium's lower too. In a real car, that's a sodium SUV going maybe 350 kilometers, where a lithium one does 400 to 600. On energy density, sodium loses. Full stop. Power tells a similar story with a twist. On a Ragan plot energy across, power up mainstream sodium sits a notch below lithium on energy, and honestly, nothing special on power. It's not a power champion. But that weird aqueous Prussian blue niche flies off into the top left corner. Tiny energy, enormous power and life. Different tool, different job. Not every battery is trying to be an EV. Now the open loop I told you to hold is the cheap material, a cheap cell? Today, no. Sodium $59 a kilowatt hour, LFP 52, because sodium's volumes are still tiny. But scale bends the curve. IRENA projects sodium toward $40 a kilowatt hour by around 2030 as capacity grows, and I'll label that clearly as a projection, not today's price. So the honest answer: not cheaper now, plausibly cheaper at scale later. Loop closed with a date, not a promise. Here the challenger lands a real punch cycle life. Manufacturers rate the best sodium cells above 10,000 charges. Cattle and BYD claim past 10,000. High-Na past 8,000. I'll attribute those to the vendors, but even conservatively, that matches or beats LFP's 3 to 8,000 and crushes nickel lithium's 1 to 2.5. For something that sits on a grid cycling every day for 20 years, this round matters far more than raw range. And now the round that finally cashes in our paradox, the cold. Watch capacity as the temperature drops. Lithium sags hard below freezing. Sodium holds roughly 90% of its capacity at minus 40 degrees. And a quick honesty flag: you'll see vendors shout minus 85 treat that as marketing. Minus 40 is the defensible number, and it's remarkable enough. But why, when sodium's ion is the big, clumsy one? Here it is. Out in the electrolyte, sodium wears a smaller, looser solvent coat and sheds it easily, even at minus 40, while lithium grips a bigger coat that's brutal to peel in the cold. Big and slow in the rock, small and nimble in the river. Both were true all along. And this is real, not a lab fantasy. In 2025, Naxtra went to production, and a Cattle-Changan car became the first mass-production sodium passenger vehicle. Na and BYD are scaling gigawatt-hour plants. But be honest about the map. The West's two big hopes, Northvolt and Natron, both collapsed in 2025. China holds over 95% of sodium capacity, and sodium is still under 1% of lithium's volume. Real and shipping, but early, fragile, and lopsided. So read the final scoreboard and read it honestly, because we earned every line. Sodium is worse at energy density, gravimetric and volumetric both, so it loses exactly where phones and long-range cars care most. And that's not a flaw someone hid, it's a heavier ion and a lower voltage. But look what it won. Dirt cheap, everywhere abundant sodium, no lithium, cobalt, or copper, 10,000 cycle lifetimes, safe enough to ship at 0 volts, and working in cold that stops lithium dead. Not best. Better at different things, which points it straight at grid storage, cheap city EVs, and freezing climates. Not your pocket. So the honest one-liner, sodium is not a lithium killer, and it's not a scam, it's a different bargain, discovered part by part on this board. And that opening paradox turned out to be the whole thesis. Big and slow in the solid, small and nimble in the liquid, which is exactly why it shrugs off the cold. We built the cell. Next time, we push it hard fast, charging, degradation, and what actually kills a sodium battery. Bring the ledger.